Okay, this is the last lesson in Module 1, Lesson 13. We're going to talk about comparing numbers in scientific notation. So we've been doing operations with them, and I've touched on comparison, but we're going to dive in a little bit deeper in this lesson. So let's just briefly look at the notes you have in your classwork here. I want to just, I'll let you read them, but I want to kind of explain what they're saying. So the first thing is if we can, we know how to compare whole numbers. So if we can reduce this task to comparing whole numbers, then we've got it kind of covered, because we know some things about whole numbers. This first inequality, I'm just going to give you an example by way of explaining it. So if I have these two numbers x and y, where x is less than y, so let's just pick one. So we've got 32 is less than 57. Okay, so that's my x and y. I'll put it here, x less than y. If I have some number z that's greater than 0, so it's not negative, it's not 0, it's a positive number, and in this situation that number is going to be a power of 10. Okay, so if I know that 32 is less than 57, so I also know that 32 times 10 to the 41st power has to be less than 57 times 10 to the 41st power. So if my exponents are the same when I'm comparing two numbers in scientific notation, if my power of 10s match, then all I have to do is compare these numbers out here. So because I know that 32 is less than 57 because they're whole numbers and I've been working with those, then I know that, so this is basically my x times z that's referred to up here is less than y times z. So that's just a basic principle of solving equations or dealing with equations and expressions. So yeah, so hopefully that is clear to you. So if my powers of 10 are the same, then all I have to do is compare the number out front. When I compare whole numbers, let's just review this. If two whole numbers have different numbers of digits, then the one with more digits is greater. So, I know that if I have the number 99 and the number 162, because 162 has more digits, it's bigger than 99, even though those individual digits are smaller, right? So more digits, greater number. And then if two whole numbers have the same number of digits and agree digit by digit until the nth place, if the digit of p, this sounds really confusing, right? In the nth plus 1 place is greater, blah, 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 then p is greater than. Let's give an example of that. So I get some room here. So what this is saying is I might have two numbers. Oh, get my pen here. So 3,281 and 3,279, say. So if I want to compare those numbers, I'm going to start at the left. They both have a 3. So then I have to go to the next place value, the next largest place value. They both have a 2. And then I compare here, an 8 and a 7. So here I see the 8 is greater than the 7, so I know that this number is greater than that number. So that's just a basic principle of comparing whole numbers. Okay, so we're going to use some of that as we talk about comparing these numbers in scientific notation. Okay, so a number in scientific notation is of the form d times 10 to the n, where our d is a number between 1 and 10, greater than 1, greater than or equal to 1, less than 10, and the power of 10 has an integer exponent. It could be positive, negative, or 0, and so those are the requirements for the number to be in scientific notation. So if I want to compare, make some comparisons, I might have two numbers where the exponents are different. Or I might have a pair of numbers where the exponents are the same, and I want to compare them. So where we're going with this lesson in the end is to realize that when we compare numbers in scientific notation, if the exponents are different, the number with the larger exponent is going to be the bigger number. Doesn't matter what the numbers out front are. Doesn't matter what these numbers are. The number with the larger exponent is going to be the larger number. But we're not going to use that yet. We're going to actually prove that. We're going to prove that through doing some examples and looking at the results, and then also by going through a mathematical proof. And then by the same token, we're going to see that if two numbers have the power of 10 equal on them, that we need to look at the decimal part of the scientific notation, and the larger number out here is going to give us a larger overall number. So that's kind of where we're going with this, and I just want to give you that so you can maybe see the purpose in some of what we'll be talking about. Okay, this example is not in your classwork, so you can take some notes on it on a separate sheet, or just watch, whatever your style. And so we're dealing with large numbers here, galaxies that are two different galaxies. M82 is 1.15 times 10 to the 7th light years away, and Leo dwarf is 8.2 times 10 to the 5th light years away, and we want to know which is closer. So what we're doing is comparing those two numbers. So we've got there, I've copied them for you. So one thing I could do is I could write these as decimal numbers. So I'm going to do this first one. I'm going to add enough zeros so that I can move the decimal place 7 places to the right. So 1, 2, 3, 5, 6, 7. That gets it right there. So that's this number, 1, 1, 5, 0, 0, 0. Right there. I'll put some commas in, and that's the distance, and that would be it's still in light years. And then the 8.2 times 10 to the 5th, I could do the same thing with. 8.2, I need to add enough zeros that I can move that decimal place 5 places. So that number would be 820,000. So these are the two numbers I'm comparing. So notice the one with more digits is the greater number. So 1.15 times 10 to the 7th is greater. Another thing I could do is to make the powers of 10 the same so that I can compare them. So that means I'm going to have to take one of these numbers out of scientific notation. Okay, so to do that, I'm going to take this first one and transform it. So I'm going to have 1.15, and now I'm going to take the 10 to the 7th and write it in two parts as 2 powers of 10. So I'm going to have, I want one of them to be 10 to the 5th, so I just have to figure out what the other one is. So the other one is going to be 10 squared to make that equal to what I had before. Okay, so then I can rewrite this. 1.15 times 10 squared is, when I move the decimal place 2 places, I get 115 times 10 to the 5th. And the other number, by comparison, is 8.2 times 10 to the 5th. So we know because these numbers are being multiplied by the same multiplier, right here, 10 to the 5th, that all I need to do is realize that 8.2 is less than 115 to realize that, once again, that M82 is further away, or Leo dwarf is closer to Earth. This is the larger number, this is the smaller number, and I've showed you two ways to do that. Either just put them directly into decimal form or adjust it so that the powers of 10 are equal. So once again, this number is no longer in scientific notation, but it has the same value as the number in scientific notation had. Okay, so that's how we're going to compare these numbers. So what I'd like you to do now is complete exercise 1 using the method that I showed you in the second example here. Instead of, not this one, not putting them into whole numbers, but try to use this method and do exercise 1. Okay, so go ahead and pause now and work on that, and then we'll work on it together. Okay, so we start by just writing the numbers. These are the two numbers that we're trying to compare. And so we want to get the power of 10s equal. So in order to do that, I'm going to take the larger power of 10 and split it up. And so I'm going to use this 2.43 times 10 to the 6th. And I'm going to write the 10 to the 6th in parts. 10 times 10 to the 5th. So it's really 10 to the first power times 10 to the 5th. And then I'm going to associate the 10 with the 2.43. And that's going to move the decimal place for just one place to the right. So I'll get 24.3 times 10 to the 5th. So that value is the same as what I had originally. But now, since the powers of 10 are equal, I've got 10 to the 5th here and 10 to the 5th here. I'm going to compare these numbers. So since 4.6 is less than 24.3, I know that the Fornax galaxy, the Fornax dwarf galaxy is closer to Earth. And so we've shown that without taking advantage of the fact that, remember, where we're going is to know that as long as the numbers are in scientific notation, these numbers out front are between 1 and 10, then all I have to do is look at the exponent. So look, it worked here. The exponent's larger. It turns out that this is a larger number, the 24.3. Okay, I've got another quick example for you, and then I'll let you do exercise 2. So this is, again, isn't in your book. There's going to be some interesting words for you here. This is an example from particle physics again. So we're talking about subatomic particles, and we're talking about that some of them are very unstable. They don't last very long. So pions have an average lifetime of 2.603 times 10 to the minus 8 seconds. And muons have an average lifetime of 2.197 times 10 to the minus 6, which has the longer average lifetime. So these are particles. You know, we know about protons, neutrons, electrons. Well, these are even smaller, crazier particles, and you could read about this. It's pretty interesting. So, but anyway, so if I want to compare these numbers, first thing I want to do, again, is to just write them out. So 2.603 times 10 to the minus 8, 2.197 times 10 to the minus 6. So again, what I want to do is to use that method where I make the power of 10 the same. So this is a little trickier maybe with the negative exponent. So I'm going to take the 2.197, and I want to break apart that 10 to the minus 6 into 10 to the something times 10 to the minus 8. So what do I need to add to negative 8 to get negative 6? That's the question here. So go ahead and think about that, and then we'll move on. Okay, so maybe you saw that adding positive 2 to 8 would give us negative 6. So what I've done here is I have not changed the number. I've just broken apart 10 to the minus 6 into 10 squared times 10 to the negative 8. Okay, so I haven't changed anything. So what I want to do now is put together the first part, the 10 squared. I'm going to multiply that times my 2.197. So in doing that, I've moved the decimal place 2 places to the right, and I get 219.7, and then I still have the 10 to the minus 8. So now I have two numbers whose power of 10 is the same. So I know, because these numbers are both being multiplied by the same number, that all I need to do is compare these. Well, clearly 2.603 is quite a bit smaller than 219.7. So the muons have a longer lifetime. I have to go back and see, okay, which one was which. The muons were the ones with 10 to the minus 6. So that is the longer average lifetime. All right, so I want to draw your attention back to the exponents. I could have looked at negative 8 and negative 6 and recognized that negative 6 is greater than negative 8 because it's further to the right on the number line, closer to 0. It's a bigger number. Negative 6 is a bigger number. So that this whole expression would be bigger because both of these are in scientific notation. Okay, so we're building evidence for that's going to be a good method to use. But let's move on. I want you to work on exercise 2 now and see if you can do this with negative exponents using the same method that I just used in that example. Okay, this example deals with subatomic particles again. The tau lepton, which has a lifetime of 2.906 times 10 to the minus 13 seconds. And the neutral pion, whose lifespan is 8.4 times 10 to the minus 17th seconds. And we want to know which one has the longer average lifetime. Okay, so you've done this problem, so I'm just going to quickly go through the solution so you can check yours. And so these are the numbers that we're trying to compare. So we want to change one of them we want to change one so that they both have the same power of 10. Now you could change one or the other. It doesn't matter which one you work on. So I'm going to change the 2.906. And so I need to know what can I add to negative 17 to get negative 13 back out. So I'm just splitting this power of 10. And so think about that. There's negative 17, there's negative 13, and the distance between them is 4. So to get from negative 17 to negative 13, I have to add 4. So that gives me this expression, 2.906 times 10 to the 4th times 10 to the negative 17. And then I'm going to use that 10 to the 4th and multiply it by the number in front so that I get some number, which ends up being 29,060 times 10 to the negative 17th. So what I'm saying is that this number here in scientific notation is equivalent to this number written as a decimal number, but a large one, times a power of 10. Okay, once I've done that, then I can compare these two numbers, the 8.4 times 10 to the negative 17, and the 29,000 times 10 to the negative 17, and realize that 8.4 is way smaller than 29,000. So the tau lepton has the longer lifetime. Okay, so this brings us to our theorem, and this is kind of the central point of this lesson. So this is our theorem, and we're going to actually prove it mathematically. And seeing these proofs, you're not going to be held responsible for doing them independently. Although there is a similar proof in the problem set, there's not one on the end of module assessment. So this is exposure for you now. In high school, you'll be required to produce some of these on your own. So let's see if we can follow along though. So given two positive numbers in scientific notation, and here's our scientific notation numbers right here, A and B. Let me just point to them. A times 10 to the m, B times 10 to the n. If m is less than n, so looking just at the exponents, then a times 10 to the m will be less than b times 10 to the n. So that's what I've been telling you, is that if the numbers are in scientific notation, and that's important, then what's out in front, the a and the b, the numbers themselves, the decimal part, doesn't matter. Only the exponent is going to determine which one's greater. And remember, the exponent is telling us the magnitude of the number. So if they're different magnitudes, then the one with the larger exponent is going to have the larger magnitude and it's going to be a larger number. Okay, so what is that? How would we go about proving that? Well, we're going to use a method similar to the examples we've been doing. So if you look here, I want to point out the structure of this theorem. So given, this is what we're given, two numbers in scientific notation, and m is less than n. And then our statement has a then. So given that all this stuff is true, then I know which number's the smaller and the bigger, okay? So there's the two parts of the theorem. Given these things, then this is true. Okay, so we're going to use the given in our proof, so we need to realize what those things are. All right, so let's look at the first step. Okay, so we're told one of the things that we're given is that m is less than n. So because m is less than n, there is some positive integer, and we're going to call that k, so that n equals m plus k. So, for example, if m is 2 and n is 5, then k is 3. There's some number that I can add to m to give me n, okay? And we're talking about the exponents now, and that's exactly what we were doing in the examples. We had to see what could we add to negative 17 to get negative 13. So that's that number that we add. Okay, because that's true, what's our next step? So I can rewrite, since I know n is equal to m plus k, I can just rewrite b times 10 to the n. That's one of my numbers that I'm comparing. I'm going to rewrite that as b times 10 to the k plus m. And just like we did before, I can break 10 to the k plus m into 10 to the k times 10 to the m. And the reason I can do that is one of those laws of exponents, right? When I have a product like this, 10 to the k times 10 to the m, I can combine it in 10 to the k plus m. Okay, so that's just a simple use of the laws of exponents that we were learning. Okay, so moving on. What I want to do is put the 10 to the k and combine that with b, because I'm trying to get two numbers that have the same power of 10. All right, so a has 10 to the m associated with it. So now my second number, b times 10 to the n, now I've expressed that in terms of 10 to the m. So I'm going to go ahead and compare these. Okay, so I'm comparing those two numbers now. I've just rewritten this one. All right, so if we can show that a is less than b times 10 to the k, so here's a, and here's b times 10 to the k, because they both have times 10 to the m on them. Where is it? I know that's all I need to compare. So if I can show that A is less than B times 10 to the K, no matter what A and B are, then I'm done. Then we'll know that A times 10 to the N is less than B times 10 to the M. Or did I have that backwards? Oh, I put those backwards. Let's fix that right now. Okay, see, I make mistakes. But that could be really confusing. So let me get my purple pen and fix that. This should be the M, and this should be the N. Okay, B times 10 to the N. Okay, so if we can show that, so all we have to look at now is this part of A times 10 to the M, and where is it? This part of B times 10 to the N. Okay, so then we'll know that. So what do we want to do now? Okay, so here's where this gets really fun. Okay, so we know that those two numbers were in scientific notation. That's one of the things we were given. So what do we know about A? Well, we know that A is less than 10 because that number was in scientific notation. So A has to be less than 10. And here's another thing we know. B times 10 to the K has to be greater than 10 because B is a number between 1 and 10. K is at least 1 because it's a positive integer. So it can't be 0. It can't be negative. So I know that some number between 1 and 10 multiplied by a number that's at least 10 is going to be greater than 10. So since this number is greater than 10 and A is less than 10, yeah, I wrote that. B is between 1 and 10. We know that A has to be less than B times 10 to the K. So since I've shown that A is less than B times 10 to the K, then I know that these numbers in scientific notation are also ordered in the same way. Okay, so this is significant because now we know that when we're given these two numbers that are written in scientific notation, all I need to do is look at the exponents. The larger exponent is going to be the larger number. And that's all that this statement says. So I'd encourage you to read it again. Maybe try to watch this segment over again so that you can follow along with the reasoning that's going on. And if not, just move on because you can use this result and know that we've proved it together. All right, so exercises 4 and 5, you can complete on your own. You're asked to compare a couple numbers in exercise 5, and then you're asked to critique Chris's reasoning in exercise 5. So go ahead and pause the video and work on those, and then come back and I'll show you some results. Okay, so what we have here are two numbers whose power of 10 is the same, 10 to the 28th in both cases. And so all we need to do is compare the decimal part of this scientific notation. And so we notice that when we start from the leftmost digit, the 9s are the same. So that tells us we need to go to the next largest place value, which would be the 10th place. So I've got 3 and 2. So it doesn't matter how many digits come after this, they'll never add up to, they'll never make this a 3. So I know that 9.3 is greater than 9.2879. Okay, so we could write it that way. And since I know that 9.2879 is less than 9.3, then 9.2879 times 10 to the 28th is less than 9.3 times 10 to the 28th. Okay, let's look at the next one. Chris said that 5.3 times 10 to the 41st is less than 5.301 times 10 to the 41st because 5.3 has fewer digits than 5.301. Show that even though his answer is correct, and it is, his reasoning is flawed. And showing him an example to illustrate that his reasoning would result in an incorrect answer. And then explain that. Okay, so I'll attempt to explain it, and you'll have your own method for explaining it. But what we need to notice is that when we can add zeros behind the decimal place like this, because they're not changing any of the non-zero digits place value. I don't change place value by adding zeros after the decimal place. Unless I'm moving some other digit. Okay, so you get that. So now I can see clearly how to compare these two numbers, that 5.300 is less than 5.301 because I follow it out. These digits are the same, these are the same, these are the same, and then finally I hit one that's different. This one's bigger, and so this whole number is bigger. And since the powers of 10 were the same, then I could make this conclusion. Okay, but it's not based on Chris's reason. So let's show him an example. And in math, we call that a counter example. If I can show him one example where his reasoning doesn't work, then he can't use it anymore. Okay, so here's an example where his reasoning doesn't work. 5.9 times 10 to the 40th and 5.893 times 10 to the 40th. 5.893 has more digits, but it's a smaller number. So if I look at this, I realize 5.893 is less than 5.9. But Chris's reasoning would have led him to say that it was bigger because it had more digits. Okay, so that's a counter example in math. So if I can show just one example where it doesn't work, then I've proven that that's flawed reasoning. Okay, exploratory challenge 2 and exercise 6 show you kind of an interesting thing, and I'm not going to go over it on the video. You have notes on this in the teacher edition if you're interested, but in the interest of time on this video, I feel like it's that I'd like to skip it and not worry about it. So I just wanted to kind of recap what the major points were for today. And to do that, let's go back to our theorem. So in our theorem, we showed that given two positive numbers in scientific notation, if m, if the one with the lower exponent is the smaller number overall. Okay, so it doesn't matter what a and b are, but they have to be in scientific notation. So in your problem set, you're going to see you're going to be asked a question about that, and it's a pretty deep question, and I encourage you to think hard about, if these numbers weren't in scientific notation, could I compare the exponents to know which one was bigger? So go ahead and work on the exit ticket and problem set, and good luck with that. And then this concludes Module 1. So you'll be doing some review, and I would encourage you to look back over the lessons and then go ahead and tackle the end of module assessment.